So, let us start from where we left last time. So, after the constitutive relationships we go to the generalized current concept. We wrote that in the instantaneous domain. So, let us write the generalized current in the time harmonic domain. It is a simple matter. So, J total we have j omega d plus j c plus j I. That is j omega epsilon e plus sigma e plus j I, and therefore, that can be written as sigma plus j omega e times E plus j I. So, we call this equation 30. So, also the equation for the total magnetic current M T is j omega b plus M I, that is j omega mu h plus M I. So, this we call this 31. So, using this, the complex form of equation 16 can be written as curl of E j omega mu h is equal to j omega mu h plus M I, sorry, with a minus curl of E equal to j omega mu h plus M I. And that can be written as z cap omega h plus M I, where this j omega mu it is captured within this z cap omega parameter. So, this z cap omega is equal to j omega mu. Also, curl of H is j t and that is equal to sigma plus j omega epsilon E plus j I. So, sigma E is the conduction current, j omega epsilon is the displacement current, and j I is the impulse current. So, therefore, I can write this as y cap omega e plus g I. We call this equation 33 with y cap omega equal to sigma plus j omega epsilon. So, in equations 32 and 33, z cap omega and y cap omega are the media parameters. It specifies the characteristics of the media. Okay. Now, we go to the concept of complex power. So, how the complex power is calculated in the time harmonic domain. So, we have considered the expressions for instantaneous power and energy in terms of instantaneous field vectors. We shall now show that similar expressions in terms of complex field vectors represent the time average power and energy in the AC fields. So, we shall write this as, let us begin with the expressions for the two quantities from the instantaneous domain. So, root 2, let us begin with the description of two quantities in the instantaneous domain. A in is 2 mod A cos omega t plus alpha, that is root 2 real part of A e to the power j omega t, where we saw this before, where A is mod A e to the power j alpha. Similarly, B instantaneous is so, we will start with the description of two quantities in the instantaneous field quantities. So, A in is root 2 mod A cos omega t plus alpha, that is root 2 real part of A e to the power j omega t, where A is mod A e to the power j alpha. Similarly, B in is root 2 mod B cos omega t plus beta, that is root 2 real part of B e to the power j omega t where B equal to mod B e to the power j beta. Now, let us multiply these two quantities, because ultimately the power is the multiplication of voltage into current. So, from that concept, if we multiply two quantities, both voltage and current are varying with time. So, if we multiply two quantities which are both varying with time and which have which are both varying with time and which has different phases, the voltage and current, what happens in the time harmonic domain and how that is related to the instantaneous domain. So, A in times B in is root 2 mod A cos omega t plus alpha root 2 mod B cos omega t plus beta. So, using the cosine rule, simply we can write this as mod A mod B cos alpha minus beta plus cos 2 omega t plus alpha plus beta. So, we call this 34. Now, we compute the time average of this product. We see that there is a time dependent term and a time independent term. So, we compute, when you compute the time average, obviously this is a cosine function. So, the time average of this will be 0. So, the time average will only be contributed by this term. So, therefore, we find out the time average of A in B in, and that will be equal to mod A mod B cos alpha minus beta. So, the contribution of this term is going to be 0. We also now note that if we perform this operation A B star, if we perform this operation A B star, then we are going to get mod A mod B e to the power j alpha minus beta and that is expanding e to the power j alpha minus beta, we are going to get cos alpha minus beta plus j sin alpha minus beta. So, we find that the real part of this term A B star is the same as the time average of the instantaneous product A in B in bar. So, we write therefore, A in B in bar is equal to real part of A B star. we name this equation 35. So, this equation is the basis for our definition for the complex power. So, we will see how. So, we know the instantaneous Poynting vector is given by E in cross H in. So, E in, if I expand that in x, y, z coordinates, will be u x E x in plus E y u y E y in plus u z E z in. Similarly, H in will be u x H x in plus u y H y in plus u z H z in. So, now see, if I perform this operation S in, it will ultimately be a product of these terms, which is similar to the product of A in B in we saw earlier. So, S in will be u x u y u z E x in E y in E z in H x in H y in H z in. So, that will be equal to u x E y in H z in minus E z in H y in plus u y minus E x in H z in plus E z in H x in plus u z E x in H y in minus each E y in H x in. So, you see now this is a sum of terms, each of which is in the form of equation number 34. It therefore follows that the time average of the instantaneous Poynting vector is equal to E in cross H in var, and that will be equal to real part of E cross H star. As we saw previously. So, if E in is root 2 mod E cos omega t plus alpha is root 2 real part of E to the power j omega t, where E mod E to the power j alpha H in is root 2 mod H cos omega t plus beta, that is root 2 real part of H e to the power j omega t. So, H is equal to mod H e to the power j beta and H star is mod H e to the power minus j beta. So, in view of this, we can define a complex Poynting vector in view of this we can define a complex Poynting vector S is E cross H star whose real part, the real part of this is the time average of the instantaneous Poynting vector, or S in time average, the instantaneous Poynting vector's time average is real part of S. So, this constitutes a very important relationship, linking up the time harmonic form with the instantaneous form of the complex Poynting vector. So, after we have found out and discussed regarding the complex Poynting vector, let us now rephrase the power conservation theorem as we learnt in the instantaneous domain. So, if we rephrase the power conservation theorem as we learnt is in the instantaneous domain, we will again begin with a different vector identity, and in this case we will write first of all starting from the Maxwell's equation in the time harmonic domain. So, this is Maxwell's equations in time harmonic domain. We will now compute this one. So, it will involve the complex conjugate, while in the instantaneous domain we had only the instantaneous quantities. So, that is equal to E dot j t star plus H star dot m t. Call this 39. So, we identify the left hand side as minus divergence of E cross H star and therefore, the equation will read divergence of E cross H star plus E dot j I star j t star. The equation will now read E dot H star plus E dot j t star plus H star dot m t is 0. We call this equation number 40. So, similar to this equation, now as we did previously to this equation, we will now find the region form. This is the point form and the equation applied to a region of space. So, this is the point form of the power conservation. So, if we apply this to a region of space, we will perform the triple integration on the left and the right. So, we will say triple integral E cross H star dV plus E dot j t star that dV equal to 0. And by using divergence theorem to this term, we will get the closed surface integral E dot H star dot d s plus triple integral E dot j t star plus h star dot m t dv as 0. So, we call this equation number 41. So, we compare 40 and 41 with 18 and 19 for the corresponding instantaneous domain. So, we call 40 and 41 expressions for conservation of complex power for a point and for a region. So, this is for a region. So, this is we write this valid for a region. So, as suggested by the point relationship, we had the point relationship P f equal to divergence of S in, we noted this in the instantaneous domain, that is equal to divergence of E in cross H in. We define a complex volume density of power leaving a point as P f cap. So, this is the complex volume density of power leaving the point. As divergence of S, that is divergence of E cross H. Now, the real part of this is the time average volume density of power leaving a point. So, the real part of P f hat is equal to P f tilde is the time average volume density of power leaving a point. Similarly, we can define a complex power leaving a region, a complex power leaving a region as big P f hat S dot d s. So, closed integral the Poynting vector dot d s, and that is equal to closed surface integral E cross H star dot d s. The real part of this is the time average power flow. So, we write real part of P f hat, big P f hat is P f tilde or the time average power flow. Okay. So, let us stop here, we will continue with the power conservation theorem.